Mr. Tyson here with video 6.3, where we will begin to discuss horizontal and vertical circles. Just a quick review of what we've talked about so far. We started by speaking about what we call centripetal acceleration, which is when an object is rotating in a circular path at a constant velocity, which we call velocity t, the tangential speed or tangential velocity, and a circular path of a radius r. We know the centripetal acceleration can be calculated with the formula vt squared over r, and that acceleration is always directed toward the center of the circular path. How is that centripetal acceleration created? It's created by a centripetal force. There must be a force pushing the object toward the center of the circle. And the amount of the centripetal force is calculated by using the formula mvt squared over r, which is just the acceleration formula with mass added into it, since we know that force is equal to mass times acceleration. So far we've seen that objects moving in circles must have a centripetal force acting upon them to create the circle, even though the object's moving at a steady speed. It's not accelerating linearly. It's accelerating centripetally to create the circle. Now, something to be clear about with centripetal force. Now, we've learned about a lot of different types of forces this year, and this is sort of a review of those: applied force, frictional force, normal force, tension force, all these different types of forces that we've learned about this year. Centripetal force might seem like, oh, we're learning about a new force, and in a certain sense we are, but it's important to understand that centripetal force is not some new type of force that we're learning about, but that its centripetal force is always going to be provided by or caused by one of the types of forces we've already discussed, being used to create a circle. Okay, so that's a distinction you have to make. It might take a little while to think about, but I'm just trying to say here that when you make a free body diagram, for instance, when we outline all the forces acting on an object, you don't put centripetal force into a free body diagram. You just put the types of forces that we've learned about so far into your free body diagram. And you look and you say, which of these forces is the one or ones that are acting to create the circle? Those forces are the ones that would be providing the centripetal force. So a minute distinction, but an important one. Okay, you're not going to put centripetal force into your free body diagrams. You're just going to analyze the forces, these forces up here, the ones we've learned about. You can analyze those forces and which ones of those are acting on the object that's moving in a circle, and you're going to say, all right, which one is providing the centripetal force? Okay, so let's take an example now. You have a 500 kilogram car driving 15 meters per second around a circular track. The radius of the track is 75 meters. What's the centripetal force acting on the car, and where does this force come from? Okay, so what do we have here? Well, let's see a little picture of what we've got going on. Here's our circular track. Its radius is 75. The car is going around it at a steady speed of 15 meters per second. The mass of the car is 500 kilograms. So from our formula, we know that we can calculate the centripetal force 1,500 newtons, right? M, mass, V squared over R. Tells us how many newtons of centripetal force are necessary to make this 500 kilogram car move in a circle at that speed. If that centripetal force is not provided, this car will not do that. It simply won't do it. It will, it'll fall off. Remember, it always wants to go off anyway into a straight line. It'll fly off in a straight line path instead. Okay, so what's actually then creating the centripetal force that is making this car move in a circle? Well, analyze the forces acting on the car. I gave you a little side view here. So what you have to imagine here is kind of like this dot is the car, and it's heading into the screen. Right? So it's moving in a circle, which means it's kind of moving in a circle, big circle like that, coming around, but it's going into the screen. What forces are acting upon it? Well, gravity's pulling it down to the ground, and the normal force of the ground is pushing it upwards, right? And since it's moving in a circle that goes into the screen, then the centripetal force must be acting to the left, right? Well, so what force is it that's actually doing that? Well, that's friction. Why does the car turn in a circle? Because the friction between the tires and the road is pushing it to the left. So in this situation here, we're saying that the friction force would be pushing inward. That's what's creating the centripetal force, friction. Notice my diagram. It doesn't have anything in it that says centripetal force. But by analyzing it, I can figure out that the only force that could possibly be providing the centripetal force is the friction. Gravity's not going in the proper direction. Gravity's pulling the car down to the ground. That's not the direction of centripetal force. Normal force is pushing up from the ground on the car. That's not the proper direction for centripetal force. Only the friction between the car and the ground could be heading in this direction and providing the centripetal force. And if you think about this, sometime in your life you've probably driven over snow or ice and you've tried to make a turn or been in a car where somebody has tried to make a turn. So they're trying to go in a curve or a circle, but the ice was too slippery and so the car doesn't do it. That's the idea. If there's ice, if you were on ice here, it would not be able to provide friction force to provide centripetal force to make a circle. And that's why you don't go in a circle. You do what they call a fishtail or you slide on the ice. All right, now, so we're talking about vertical and horizontal circles. That was an example of a horizontal circle. What's the difference? Well, basically the difference between horizontal and vertical. These cars going around this track, they're on the ground and they're rotating around the track in what we would call a horizontal circle. In other words, the plane of the circle is horizontal to the ground. This girl who's spinning this ball in the air, it's going around like this. Again, the circle, this plane of the circle, the flat surface of the circle is parallel to the ground, so it's horizontal. Vertical circles, like a tire on a car. Now that rotates in a vertical plane, okay, and so does a Ferris wheel. This is what we would call a vertical circle. Now you might think, well, they're still both circles. What's the difference? Well, okay, so here's the difference. In a horizontal circle, gravity cannot provide any of the centripetal force, just like we just did with the car. Okay, these cars, they're traveling a horizontal circle, right? We just showed that the centripetal force is being provided by friction. We said, here's the friction. Now I got to get a thinner marker here. Let's see, how about this? So we said that the friction force is providing the centripetal force. Gravity's going down, and normal force is going up. But the point is, there's no way that gravity could ever help provide any of the centripetal force in a horizontal circle, because gravity in a horizontal circle is always going to be pulling downward, straight down, which can't help at all toward the center of the circle. Okay, so that's a fact we need to know about a horizontal circle. Now the girl who's twirling this thing here, this is interesting to study because this circle she's making is not on the ground, but of course gravity is still acting. So if you look at it, you'll see that the girl is twirling the ball, in her hand, but that the ball is slightly below. You see that the string has a bit of an angle to it? Okay, let's just kind of draw it across here. I'll draw this parallel to the ground. So there's an angle between where the ball is rotating in the circle and where she's holding it with her hand. The faster you rotate this ball, the less of an angle there'll be, but actually you can't rotate the ball fast enough so that there's no angle. There's always going to be an angle because gravity is always pulling down on the ball. The string, the force that's in the string, which of course we call tension, right, that is providing both of the forces that are necessary to keep the ball rotating in the air in a circle. Think about that, in the air. Well, how can you be in the air? How can the ball stay in the air? Because gravity's pulling it down. It can only stay in the air if there's another force pulling up on it, okay? And that force is provided by part of the force in the string. Remember, the force in the string is acting at an angle. That means that it can be broken into two parts, a vertical part and a horizontal part, and we know how to do that with sines and cosines. The vertical part of the force in the string is counteracting the gravity. Here it is over here. Here is just move it, right? See how it's exactly the same as the gravity force. They're canceling each other out, and that's why the ball stays in midair and doesn't fall down. But the other part of the force in the string, which is the part of the cosine part, the horizontal part, that is providing the centripetal force. That's why the ball can move in a circle. Okay, so let's take a little example of a problem that applies that idea. Here's the girl spinning the 3-kilogram object in a horizontal circle. The radius is 1.3 meters, and she's going at a constant speed of 5. The angle between the string and the horizontal is 30 degrees. Find the force of tension. Right, so the picture we just looked at, right? Here's the string, she's pulling on it, and the question is find the force of tension in that string. All right, well, we know that there's a 30-degree angle. So therefore, our 30-degree angle comes in here, 30 degrees. So we know that the force of the string, whatever it is, multiplied by the cosine of 30 degrees will give us this part, this component of the force of the string. There it is, the force of tension in the string multiplied by the cosine of 30 degrees will tell us the centripetal force, right? Just talked about that in the previous picture. Now put that into a formula. If that's the centripetal force, right, if that's what the centripetal force equals, then it must equal mv squared over r, because we know the amount of the centripetal force can be calculated with this formula. All right, so now I have an equation. I know that these two things equal each other. I can solve to find the force of tension, which is the question. So divide both sides by cosine of 30, and then get your calculator out and calculate your answer. 66.6 newtons of force of tension is required in the string, so that the component in this direction will be enough to create the circle, and the component in this direction will be enough to counteract the force of gravity. So now, that was horizontal circles. Let's talk a little bit about vertical circles. In those, gravity helps provide centripetal force when the object is at the top of the circle, but it works against centripetal force when the object is at the bottom of the circle. Okay, now think about a circle, like a tire, or an object that's on a tire, right? And it's going around in a circle vertically on the ground, rolling down the ground, or just kind of rotating. When you're at the top versus when you're at the bottom. We're not going to go in between because that gets to do with cosines and sines. We're just not going to get that much into it. But we're interested in two specific locations on a vertical circle, the top and the bottom. At the very top, here's my analysis of the forces acting on this object. The force of tension, right, I'm going to imagine that I'm rotating this on a string, okay? So we'll call it tension force. So I have a string and I'm rotating it in a vertical circle. At the top of the circle, the force of tension is me pulling on the string, and the force of gravity is pulling down on the object. Both of those forces are acting on the object. So notice that they're working together in the same direction. So that if we combine them, the force of tension plus the force of gravity, putting them together, that is what's providing the centripetal force. Okay, but what about at the bottom? Now you rotate on your string and you get to the bottom of your circle. Well, at the bottom of your circle, you're pulling upwards on the string, because you're in the middle here with a string. So you'd be pulling upward on the string, and the force of gravity is still pulling down. So notice at the bottom of the circle, they work against each other. And when forces go in opposite directions, we subtract them. We need enough force heading toward the center of the circle to provide centripetal force. But gravity's heading the other way, so it's working against us at the bottom of the circle. So at the bottom of the circle, we can say that the centripetal force is equal to the tension force minus the force of gravity. All right, so notice the difference between top and bottom. It's really just a difference of the gravity's direction. Okay, you're going to add it at the top, you're going to subtract it at the bottom. All right, now, how can we use that in a problem? So let's take an example. A person swings a 2-kilogram object around in a vertical circle with a radius of 0.7 meters at a steady speed of 4 meters per second. What's the tension in the string at the top and the bottom of the circle? Okay, so let's take a look at the top of the circle. We just said the centripetal force at the top, where gravity will help, okay, is equal to the force of the tension in the string plus the force of the gravity pulling down. By the way, before I forget to say it, if you ever have tried rotating something on a string in a vertical circle, what you may notice if you do it for a while is that when you get to the top, when it's at the top, you'll feel less pull in the string than you do at the bottom. Okay, that's an example of how, at the top, you're going to feel less tension in the string because gravity's helping you to make the circle. At the bottom, you're going to need to pull harder on the string because gravity's working against you making the circle. Okay, so that's something you can test out for yourself. All right, so back to the problem. The force, centripetal force, is equal to the tension force plus the gravity force when it's at the top of the circle. So I'm simply going to plug in the numbers that I know to solve for what I don't know, which is the tension. So I want to know the tension force, so I minus the gravity force from both sides. So I can see that the tension force is equal to the centripetal force minus the gravity force. This is simply that formula from the previous page. I'm taking it and I'm moving things around because the thing I'm looking for right now is the tension force. So the tension force equals the centripetal force, mv squared over r, minus the gravity force, which remember is the weight of the object. We didn't get the weight, we got the mass. 2 kilograms times 9.8 to turn it into the weight of the object, which is the force of gravity. And then solve. 26.1 newtons is our centripetal force. How about at the bottom? Well, at the bottom, the only difference, remember, is that now gravity is working against the centripetal force. So the centripetal force equals the tension minus gravity at the bottom. So if I want to find tension by itself, I would add the force of gravity to both sides. And the force of tension equals the centripetal force plus the force of gravity. So to solve for the force of tension now, it's mv squared over r, the centripetal force, plus 2 times 9.8, which is the gravity force. And that tells me that at the bottom, I will have to pull 65.3 newtons upward on the string to keep the object rotating in the circle. Okay, what about other things that go in vertical circles, like a roller coaster? You've probably been on one of those roller coasters that goes upside down. Think of that as a circular object, right? So we have a roller coaster built to go around in a vertical circle, and the weight of the coaster is 1,000 newtons. Notice right off the bat they gave me the weight, so that's force of gravity, 1,000 newtons. I don't have to use 9.8. And there must be 1,050 newtons of centripetal force to keep the coaster moving in a circle. Notice also that in this problem they've given me the centripetal force in newtons. That means I don't have to use mv squared over r. I already know how much centripetal force is necessary. What is the normal force from the track when the coaster is at the top of its path? Well, okay, so a roller coaster is not attached to a string. So what keeps a roller coaster from flying off when it's at the top of the track? Well, obviously it's connected to the track, but what keeps it moving in a circle? Well, in this case, it's not tension force, it's normal force. Normal force at the top of the roller coaster is the track. The track, it's kind of like the floor, right? But at the top of the circle, it's pushing upward. The roller coaster is pushing upward on the track, which means normal force will always point the opposite direction. The normal force pushes downward. So this is the force of the track pushing down on the roller coaster car. We still have gravity, which is pulling the roller coaster car down. So still, the two forces are acting together to create the centripetal force, which is necessary to keep the roller coaster moving in a circular path. So it's really still the same formula, even though there's no string attached. It's the centripetal force is equal to the normal force plus the gravity force, right? And they're working together in the same direction. So the centripetal force was given to us. We don't have to calculate it. It's 1,050. The gravity force of the roller coaster was given to us. We don't have to calculate it. It's 1,000 newtons. And so simply solve through for the normal force necessary, which is 50 newtons. There's a couple of examples there of horizontal circles and vertical circles that you can now take and apply.